Hey y'all, welcome back. We are doing chapters 6.1 and 6.2. This is lecture 20 and we're going to be learning about matrices. So let's go ahead and jump right in. So just a little introduction first. A system of equations can be represented as a rectangular array of elements and it's called a matrix. A matrix can be used to represent a system of linear equations written in standard form. To do so, we extract the coefficients of each term in the equation to form an augmented matrix. For example, I'm going to show y'all how we're going to write this system of equations as an augmented matrix. So what we need to do first is identify the coefficients of each variable. So you notice here in the top equation, there is no variable z. So we would consider that having a coefficient of 0, since 0 times z is equal to 0. So now, writing the matrix, you need a large bracket. So my first equation, the x coefficient is going to be 3. The y coefficient is going to be 2. The z coefficient is going to be 0. And then a vertical line will represent the equal sign. And we have 5 as my constant. Okay, second equation. So now we're looking at this one. We have a 1 in front of the x, a -1 in front of the y, a 3 in front of the z, and equals 4. And then the last equation, we'll have 2, and then 1, and then 1, and then 4. So this is the augmented matrix. Typically, you do not write the variables on the top. I just did that as a demonstration. So the actual solution would be just this matrix here. What's your solution? All right, let's keep going. So now we want to go the other way. We want to take our matrix and write it instead as a system of linear equations. So remember, if this represents x and then y and then z, and then this is the equal sign. So that means my first equation is going to be 1 times x plus 0 times y plus 0 times z equals 6. Then I have 0x plus 1y plus 0z equals -10. And then 0x plus 0y plus 1z equals 4, which just means I have x equals 6, y equals -10, and z equals 4 as my equations. All right, next. So this is going to be x, this is going to be y, and then we have the equal sign. So we'll have 1x minus 2y equals 6, and 3x plus 1y equals -10. And typically we don't write the ones as coefficients. I'm just doing it to be clear for the first bit here. So there are my system of equations. There is my system, yeah. Okay, next we're going to talk about row operations. So generally we're going to use an augmented matrix to solve a system of linear equations in the same way that we use the addition method when we're just solving like from chapter 5. The same operations performed on a matrix are called elementary row operations. So the first example of an elementary row operation is going to be to interchange equations. So all that's going to mean is we're just going to swap the way that they're written. So this system here is the same as if I wrote x plus 2y equals 5, -3x minus 5y equals -13. So all this is saying is that it doesn't matter which comes first, right? All right. Next, we want to multiply an equation by a non-zero constant. So essentially this would be if I choose the second equation, let's just say I want to multiply by 2. So I want to multiply the second equation by 2. We know that we are able to do this because we do this when we do the addition method, right? We'll multiply one equation by a constant in order to be able to add or subtract the equations to cancel a variable. So I can always multiply any equation by a non-zero number and it's okay. The last bit is going to be to add a non-zero multiple of one equation to the other equation. So again, that's like the actual addition method. So let's say I want to do 3 times the bottom equation and I want to add it to the top equation. So that means I would have negative 3x minus 5y equals negative 13 plus 3x plus 6y equals 15. And I get y equals 2. So we're going to talk about how to do these operations in matrix form. So the first thing that we're going to do is interchange the equations. So what we want to do is exchange row 1 with row 2. So that means our new matrix is going to be 1, 2, augmented 5, and the bottom row negative 3, negative 5, negative 13. And that's all. So all we did was swap the rows. Next, we want to multiply an equation by a non-zero constant. I'll just do the same thing that I did up here. So 2 times row 2 is going to be the new row 2. So that means we'll have negative 3, negative 5, negative 13 because we're not changing row 1. And what we're doing is multiplying row 2 by 2. So it gets us to 2, 4, 10. All right, next what we want to do is add a non-zero multiple of one equation to another equation. So for that, what we're going to do is add 3 times row 2 plus row 1. That's going to give us our new row 1. All right. The bottom row 2 is not going to change. And we're going to add 3 times the bottom row to the top row to get our new top row. So if we multiply the bottom by 3, that would get us 3, 6, 15. We want to add that to the top row. So 3 minus 3 is 0, and then 6 minus 5 is 1, and then 15 minus 13 is 2. So these are called row operations. All right, let's move on. So next example is, given the following matrix, perform the elementary row operations. So the first thing we're going to do is exchange the first row with the second row 1 with row 2. So that means we're going to have 1 for negative 1, and then augmented 9, and then 4, 3, 0, 5, sorry, that's a 9, and then 2, 0, negative 3, negative 8. Okay, the next thing is going to be, we want a quarter of R1 to be our new R1, so our new row 1. So that is going to be, so if we look at R1, we have 4, 3, 0, and 5. So what we're going to do is just take a fourth of all of those numbers. So 4 divided by 4 is 1, and then 3/4, and then 0, and then we'd have 5/4. Okay, and then nothing else changed. All right, last, we want to do negative 2 times row 2 plus row 3, and that's going to be our new row 3. So the negative 2 row 2 is going to be, that's negative 2 times this middle row. So that'll be negative 2, negative 8, 2, and negative 18. and we're adding that to our row 3, which is that 2, 0, negative 3, negative 8. So that means our new row 3 is going to be 0, negative 8, negative 1, negative 26. And the rest of the matrix is not changed. All right, so these are row operations. So just performing the given task. All right, let's keep going. The next thing we need to talk about is reduced row echelon form. So a matrix is in reduced row echelon form if it satisfies the following condition. The first one being any rows consisting of entirely zeros are at the bottom of the matrix. That means you cannot have something like 0, 0, 0, 1, 1, 1, 2, 2, 2, okay? All the zeros need to be at the bottom. The second one is for all other rows, the first non-zero entry is 1. This is called the leading 1. Number 3, the leading 1 in each non-zero row is to the right of the leading 1 in the row immediately above. And a matrix is in reduced row echelon form if it is in row echelon form with the added condition that each row with the leading entry of 1 has zeros above it. So this is a lot of words. I'm going to just draw you some examples. So we could have 1, 0, 0, 1. We could have 1, 0, 0, 0, 1, 0, 0, 0, 1. So you can see that we have leading ones are the ones going down the diagonal. So these and these are called the leading one. And it's like a step stool. They always have to go on the diagonal. So you can't have like a 1 here in this spot. That's not correct. The ones have to be on the diagonal from left to right. So after writing an augmented matrix in reduced or echelon form, the corresponding system of linear equations can be solved using back substitution. So essentially, if we get down to where we have 1, 0, 0, 0, 1, 0, 0, 0, 1, and we have something like, I don't know, 3, negative 1, 2, then that would mean we could have x equals 3, y equals negative 1, z equals 2, since this was the x column, the y column, and the z column. We're going to move on. So we're going to solve a system using Gaussian elimination. And I've already put it into the matrix for you so that we can skip this step. So our goal is to get the 1, 0, 0, 0, 1, 0, 0, 0, 1. That's the goal. All right. So the first thing I'm going to do is switch row 1 and row 2, because row 2 has a 1 in it, and I want that to be up here, right? I want the first, see, I want to match this. The top left, I want that to be a 1. So what I'm going to do is, so first step is row 1 switching with row 2. So I'm going to have 1, 2, negative 4, negative 3, 3, 7, negative 15, negative 12, negative 4, negative 6, 15, 16. All right, the next thing I'm going to do is start to eliminate the numbers in the first column, right? So like the x column, because if you notice here, I want a 0 and then another 0. So what I can do is I can multiply negative 3 times row 1 and add it to row 2 to get my new row 2. That way I'll have negative 3 times this 1, and negative 3 plus 3 is 0, so I will eliminate this 3. Then I want to eliminate the negative 4 in row 3, so I'm going to multiply by 4 times row 1, and I'm going to add that to row 3 to get the new row 3. So then my new matrix is going to be, well, I still have 1, 2, -4 augmented with -3. And then I'm doing -3 times row 1 plus row 2. I'll show some scratch work here. So -3 times row 1 plus row 2 is going to be, we'll have -3 plus 3, which is 0. Then we'll have -6 plus 7, which is 1. And then we'll have -3 times -4 is 12. And then -15 is -3. And then -3 times -3 is 9. -12 is -3 as well. So it gives me 0, 1, -3, -3. And what's really extra convenient is I already have a 1 in my second row, which is fantastic. Next, I can show some scratch work on 4 row 1 plus row 3. So that's going to be, well, 4 times 1 is 4, -4 is 0. And then I have 4 times 2, which is 8, -6 is 2. And then we'll have 4 times -4 is -16 plus 15 is -1. And then we have -12 plus 16, which is 4. So then my new row 3 is going to be 0, 2, -1, and 4. Okay, so what we're going to do next is try to get rid of the 2 in row 3 because we want a 0 there. How we're going to do that is we're going to do -2 row 2 plus row 3 is going to give me my new row 3. So that means I'll have my top row is not changing. So I'll still have, actually, here, let me, 1, 2, -4, -3. My second row is also not changing, so it's 0, 1, -3, -3. Then I'm going to multiply -2 times the second row, add it to the third row, so that's going to be 6 minus 1, which is 5, and 6 plus 4, which is 10. Then the next step I need to do is make this into a 1, so it's going to be 1/5 R3 is my new R3. And that's going to be 1, 2, -4, augmented -3, and then 0, 1, -3, -3, and then 0, 0, 1, and 2, because 10 divided by 5 is 2. All right, next I can start to make that top right corner of this bit, I can start to make these 0. So I can do -2 row 2 plus row 1 is my new row 1. And then I can also do 3 row 3 plus row 2 is my new row 2, which is going to get me, let's see, so it's going to be 1 and then 0, and then -2 times -3 is 6, minus 4 is 2, and then 6 minus 3 is 3, and then 0, 1, 0, and then 2 times 3 is 6, minus 3 is 3, and lastly I have 0, 0, 1, 2. The last step is I'm going to do -2 row 3 plus row 1 is my new row 1. So that is going to be, when I get 1, 0, 0, then I'll have -2 times 2 is 4. I'm sorry, -4 plus 3 is 1. -1, sorry. And then 0, 1, 0, 3, and then 0, 0, 1 with a 2. So that means my solution is x equals -1, y equals 3, z equals 2. Or as a point, -1, 3, 2. All right, so my solution to the system of equations is -1, 3, 2. Moving on. When we studied systems of linear equations in 2 and 3 variables in chapter 5, we learned that a system may have no solution. Such a system is said to be inconsistent, and we recognize an inconsistent system if the system reduces to a contradiction. All this is saying is when you put it into reduced row echelon form, you can't have a contradiction. So I went to put this into a matrix for y'all so that y'all didn't have to do it. However, I do have an error because this is a negative 2y. This should actually be a negative 2 here, which is my bad. So it's negative 2. So what we need to do is 2 times row 2 plus row 3 gives us our new row 3. So that's going to be, let's see, so 2 times row 2 will be 0, 2, 10, 36. And we're going to add row 3, which is just negative 2, negative 10, 20. This is going to be our new row 3. So this is new row 3 is 0, 0, 0, 56. So that means we'll have 1, negative 3, negative 17, negative 59, 0, 1, 5, 18, and 0, 0, 0, 56. So what's wrong with this is that each of these represent X, Y, and Z, right? So that means this is saying that 0x plus 0y plus 0z equals 56, which would imply that 0 equals 56, which is false, right? So that is why this system would be an inconsistent system, is because we're getting 0 equals 56. So whenever you have, whenever you're doing reduced or echelon form and you're getting all zeros here, but you're still getting a number here, it is an inconsistent system. All right, let's keep going. Now we're going to do some dependent equations. So what we want to do is essentially just put this into reduced echelon form. So this should say 100. Just killing it with the typos today. But anyway, I'm going to rewrite these equations. Specifically this bottom one, because we want it in terms of like negative x plus 3y equals negative 4. We want the x's and y's on the same side. So that means my matrix is going to be 25, negative 75, 100, negative 1, 3, negative 4. I'm going to do 1 over 25 row 1 is the new row 1. Since we want this spot right here to be 1, we want leading ones. So that means I'm going to get 25 divided by 25 is 1. 75 divided by 25 is 3. 100 divided by 25 is 4. On the bottom row, nothing changed. However, if I add now, if I say, okay, row 1 plus row 2 is going to be the new row 2. Can y'all see automatically that everything's going to cancel because I have 1 minus 1, negative 3 plus 3, and 4 minus 4. So that means I'm going to have 1, negative 3, 4, 0, 0, 0. So then how we would write this as a solution set is going to be, you can write it as like an equation of x. This would translate to 1 minus 3y equals 4, right? Oh, I'm sorry. This would translate to x minus 3y is 4, not 1. So if I move 3y to the other side, I have x equals 3y plus 4, which means that if I were to write it as a point, I could write it as 3y plus 4 comma y. So it would be x comma y, and this is what x is over here. So that means my solution set would be 3y plus 4 comma y, such that y is a real number. Moving on to an example with 3 variables. So the first thing we're going to do is write this as a matrix. So that is going to be big bracket. We will have 1, negative 4, 7 augmented 14. Second row is going to be -2, 9, -16, -31, 1, -7, 13, 23. The first thing that we are going to do is add 2 times row 1 plus row 2 to give us our new row 2, because we want this to be a 0. The next thing that we are going to do is going to be negative row 1 plus row 3 gives us our new row 3, because again we want this to be a 0 so we can be in reduced or echelon form. So that's going to give us 1, -4, 7, augmented 14, because row 1 did not change. Row 2 is going to change to 0, 1, -2, -3, and row 3 is going to change to 0, -3, 6, and 9. The next thing that we are going to do is 4 times row 2 plus row 1 is our new row 1. At the same time, I'm going to do 3 times row 2 plus row 3 is the new row 3. So our new matrix is going to be 1, 0, -1, augmented 2, then 0, 1, -2, -3, and then 0, 0, 0, 0. Because row 2 times 3 is going to cancel out row 3. Next, I am going to write an equivalent system because there is nothing I can do to make these two numbers 0. I don't have this third variable to cancel them out this time. So that means what I'm going to have is x minus z equals 2 and y minus 2z equals -3. And then we have 0 equals 0, which just means nothing. So essentially you want to express both of these in terms of z, because z is going to be what we call a free variable, since we have this 0 equals 0. So z can be anything it wants to be. X and y are the ones that have restrictions. So that means we'll have the first equation will be, now what we want to do is express x and y in terms of z. So that means we'll have x minus z equals 2 is going to be x equals 2 plus z, and y minus 2z equals -3, which is going to be y equals 3, -3 plus 2z. So that means our solution set is going to be the point x comma y, which is 2 plus z, comma, -3 plus 2z, since this is my x and this is my y according to what my matrix told me, comma, oops, I forgot my third variable. This is a 3-variable equation, comma z, such that z is any real number because z is a free variable. Z can be anything. However, x and y have restrictions that was told to us by our matrix here. Moving on. So let's go ahead and just get started. What we're going to do is first set it up as a matrix. So we'll have 3, -8, 18, augmented 15. On the bottom, we'll have 1, -3, 4, 6. So the first thing that I'm going to do is, can you guess? Looking at it, do you remember the goal? We want a 1 here, right? So the first thing I'm going to do is switch these. So I'm going to say row 1 switching row 2. So that means my new matrix is going to be 1, -3, 4, augmented 6, 3, -8, 18, 15. So now I've got my 1. Sweet. The next thing I want to do is make this one a 0. So that means what I'm going to need to do is -3 times row 1 plus row 2 gives the new row 2. So that is going to be, my row 1 didn't change, and I will have 0. And then I will have a 1, and then a 6, and a -3. Last, I want to get as many zeros as I can, so I'm going to try to make this one a 0 next. So what I'm going to do is 3 times row 2 plus row 1 gives my new row 1. So that means we're going to have 1, 0, 22, -3. And on the bottom row, it didn't change, so we still have 0, 1, 6, and -3 again. All right. Now, we can't really simplify any further. If we did, it would kind of get gross because we'd have fractions. So we're going to accept this and rewrite it as a system of linear equations, which would give us x plus 22z equals -3, and y plus 6z equals -3. And the last thing we're going to do is just write a general solution where we express them again both in terms of z. So that means we have x equals -3 minus 22z and y equals -3 minus 6z. So I always write my points as x comma y comma z. So that means my solution is going to be -3 minus 22z comma -3 minus 6z comma z, such that z is any real number. And that's it. Moving on to another example. Now I want to solve a system of equations. Again, we're going to use matrices. However, this one might work out a little bit nicer. We are going to find out. So I'm going to have, let's see. Let's just go ahead and do row 1 plus row 2 is going to be the new row 2. And let's do -2 row 1 plus row 3 is going to be the new row 3 as well. So then what we will have is 1, 2, 3, 6, and zeros, which is really nice because that means we only really care about this one equation, which is going to be x plus 2y plus 3z equals 6. And then we'll have, so this is going to be 0 equals 0 and 0 equals 0. So we're going to have y is free and z is free. They don't have any restrictions. X is the only one with restrictions. So then we'll say x equals 6 minus 2y minus 3z. And then our solution set will just be 6 minus 2y minus 3z comma y comma z, such that y and z are any real number. And that is it. Thank you all for watching this lecture.